Hi everyone, welcome back to Math 261. This is Scott. Let's get started. So what we are going to be taking on at this point is Chapter 3, in which we'll be making a new friend and seeing what it has to offer us. And that new friend is determinants. So there's going to be three major legs to this stool. There's going to be how we actually calculate a determinant, and then what the determinant actually determines, and then why we calculate determinants, what use they have for us in this class, and actually we'll discuss a little bit the use that they have in other classes as well. So right here we are just introducing determinants. So this is an introduction to determinants. All right. So first off, what we are talking about is a square matrix. We must have a square matrix, otherwise the determinant is not defined. So the setup here is that we will have a square matrix A. So A is n by n, in other words, square. There is no definition of a determinant that applies to a matrix that has an unequal number of rows and columns, so it must be square. Okay, so now our approach is going to be basically a recursive one. So our approach. We're going to work our way from simpler matrices into more complicated ones. So what we're going to do is we're going to figure out how to find or I'll just tell you how to find the determinant for small matrices, and then we'll discuss how to extend that to bigger matrices. So the approach is going to be to define the determinant for small matrices. For small matrices, and use this to get the determinant of larger matrices. So the notation here, the notation that we'll use for the determinant is basically like this. So we'll either write det of A or just the absolute value of A. And in particular, if we are talking about a matrix whose entries we know, then we can indicate the determinant by bars instead of square brackets. So determinant of A, or absolute value looking thing of A, and in particular, if we had a matrix. So for example, if A was a little 2 by 2 matrix, then we could write the determinant of A, and so we use these. So these bars indicate a determinant. So we're going to start small and work our way up. So first off, if A is only a 1 by 1 matrix, it's kind of a special case. It's the smallest a matrix could possibly be. So is 1 by 1, then that means A is just equal to one single entry, and the determinant of A is just that entry. Okay, too easy. Let's work our way up. So if A is 2 by 2, and this is probably something you've already seen in some context or another. This is 1 by 1. Looks like it's a absolute value of x. 1 by 1. Alright, 1 by 1. If A is 2 by 2, then that means A has the form A, B, C, and D. And then the determinant of A is equal to AD minus BC. Now we've already seen this particular expression before, back when we were talking about the inverse of a 2 by 2 matrix, and this is called, and this is the determinant, and you've probably seen it before, but it's basically, downward, downward along the main diagonal minus the skew diagonal. So, so it's AD minus BC. So it's So that's just like a little legend. Okay, now if A is any bigger than that, then we need some more notation. So if A is bigger than 2 by 2, if it's 3 by 3, 4 by 4, etc. is larger, we use what is called cofactor expansion. And here's how that works. So cofactor expansion involves expanding along the cofactors. And in particular, so the way this works is as follows. So we'll build it up. So what we do is we first find matrix A, I, J. And this represents the submatrix you get if you take row I and column J out of A. So this is the submatrix. Obtained. By removing row I and column J from A. So for example, let's say we had A equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Then let's say we wanted the submatrix A2, 3. So that means remove row 2 and column 3. So then row 2, column 3 are gone. So column 3 is gone, so that means 1, 2, nothing. Row 2 is gone, and then 7, 8. So that's the submatrix. It's an ingredient in cofactor expansion. And then the actual cofactors are this. So we write C, I, J. This represents the IJ cofactor. And the way that is defined is Cij is equal to -1 to the I plus j times the determinant of that little submatrix we just made. So A2, 3, or A, in this case, ij. So, again, for example, so with the above A, C2, 3 would be -1 to the 2 plus 3 times the determinant of the 1, 2, 7, 8. So in other words, it's going to be -1 to the 5th, so it's going to be -1 times, and then 1 times 8 minus 7 times 2. And so in other words, it's going to be 8 minus minus 14 is negative 6 times negative 1 makes positive 6. Okay, then once we have this, then the formula for cofactor expansion is the following. So cofactor expansion. So cofactor expansion works as follows. So choose either a row or a column to expand along. So choose any row or any column to expand along. And we'll describe this a little bit more when we talk strategics, but what you would be looking for is any row or any column that has a lot of zeros. So then suppose in case A, let's say we chose a specific row. So let's say we chose row K. Then the determinant of A is equal to the sum, and this is going to be J equals 1 to n of A Kj times C Kj. So if we chose row K, that's how it would be. Or B. Let's say it was column. And we could use K again, but just to make sure it's nice and clear, we'll say column L. So determinant of A is equal to the sum as I goes from 1 to n of A I L C I L. So what happens is we choose either a row or a column to focus our attention on, and then we move down the line and we actually calculate the cofactors, which are the determinants of the smaller matrices that we make when we delete selectively along the line each row or column of the matrix, and we multiply by whatever the entry of that was. So this is a very abstract way to look at it. It's the technical definition, but how this actually works in practice is like so. So how this works in practice. Is as follows. So first off, the signs, the -1 to the I plus j, that is just going to be either 1 or -1, all depending on whether the row plus the column makes an even or an odd number. So first off, the signs of the cofactors, that's the -1 to the I plus j. So the signs of the cofactors will basically be this checkerboard pattern. Plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, etc. And then down here, minus, plus, minus, dot, dot, dot. And the important thing about it is that it always begins with a plus in the upper left corner. That's entry 1, 1. So that's going to be -1 to the 2, which is going to be 1. So then we just have the alternating entries, either plus or minus. So this is the checkerboard, and that's enough. And then oops, just and it's always going to end with a plus in the bottom corner. So it's like the reason why it's called checkerboard pattern is because it resembles a chess or a checkerboard in its alternation of black and white. Only in the case of these, what we are talking about here is that first factor in the cofactor. So then choose the row or column with the most zeros to expand along. So if there are any zeros, you wanna focus in on them. Look for zeros. Zeros help. And then what you do is you go down that column or across that row, and you just use the checkerboard to indicate if it's going to be a plus or a minus. And then it's just going to be the entries, the entry of that times the determinant of the submatrix that you're creating. So then move along that row or column and multiply. Multiply each of the entries by the corresponding cofactor, and that's with the sign indicated by the checkerboard. So, for example, let's just go back to the old A equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Now here we do not have any zeros to choose from, so just out of thin air, I randomly choose I'll just say this column, and this was just chosen completely arbitrarily by me just now in a fit of caprice. There it is. It's the one I chose. So for no reason in particular, I just happened to choose this column just so we'd see how it all works. So I chose this. This is just a commentary. This column for no particular reason. This was just for illustration. So if you're looking at this and you can't think of why I would have chosen that, it's just so you can see how it works. Just for illustration. Okay, well then, here's how it would work. So the determinant of A would be, so we just go down the line here. So according to checkerboard, plus, minus. We take the entry, the 2. And then what we do is we make the rest of the cofactor here by removing column 2 and first row 1, then row 2, then row 3. So first removing row 1, what that leaves us with is 4, 6, 7, 9. And then we have, according to the checkerboard, a plus. That's going to be 5 times 1. So now I'm removing row 2, column 2. So it's going to be 1, 3, 7, 9. And then minus again, according to the checkerboard. And we're going to have 8, which is the entry, times the determinant of the result of deleting row 3 in column 2. So it's going to be 1, 4, 3, 6. And then each of these is a 2 by 2, so I reduced the problem down to a simpler case that I can then just do by the little formula. So it's going to be minus 2 times 4 times 9 minus 7 times 6 plus 5 times 1 times 9 minus 7 times 3 minus 8 times 1 times 6 minus 4 times 3. So I wouldn't ordinarily, in practice, write out all these steps, but here you'll just want to know where each of these numbers is coming from, so that's why I'm writing it in this case. So what do we have here? We have 36 minus 42 is going to be negative 6 times negative 2 is going to be positive 12. Here we're going to have 9 minus 21, so that's going to be negative 12, plus, or times 5 is going to be negative 60. And then we're going to have 6 minus 12 is negative 6, times negative 8 is going to be plus 40. All right, everyone. My camera cut out there for a second, so a couple seconds of video were lost. But I said 48 there, and then you add those all together, and you get a number, and that number is 0. Now, what does it all mean? What is this all for? That's a question that we'll be tackling in a bit, but for now, let me just say that the determinant being or not being 0 is of the utmost importance to us. So, that's how you calculate that. Now, for bigger matrices, the whole process is recursive, by which I mean you take what is a bigger problem and break it down into smaller ones until you get down to the basement level, which we can do, which is a 2 by 2 matrix. So for larger matrices, we work recursively down to the 2 by 2 case. So for example, let's say we had as a 4 by 4 matrix. So let's say A equals, let's go 3, 6, 3, 1 for the first column. And then the second column, let's go 2, 5, 0, 0. And then for the third column, let's go 4, 7, 1, 0. And then for the fifth column, let's just go 1, 1, 2, and 0. So looking at this, strategically speaking, it is vitally important for us to find the row or column that has the most zeros. So look for the one with the most zeros. So in particular, row 4 is our best bet here. So this is our choice. So technically, mathematically, you could row reduce along any row or column, or sorry, you can cofactor expand along any row or column. However, the work is much easier if it is plentiful in zeros, and here's why. So then the determinant of A will be, so use the checkerboard, plus, minus, plus, minus. And you don't need really to sketch out the whole checkerboard, really just the checkerboard along the indicated row, but it never hurts. Also, it's fun. So the checkerboard here tells us that we are going to be starting with negative, then positive, then negative, then positive. So negative, and then 1. And then what happens is we have the minor, as it's sometimes called, which is the determinant of the submatrix. So remove column 1, row 1 from consideration, and that is what we have left. So we have 2, 4, 1, 5, 7, 1, and 0, 1, 2. Now here is where the payoff of the extra zeros comes into play, plus 0 times something, doesn't even matter what, because it's being multiplied by 0. So something, don't know, don't care, minus 0 times the determinant 0 of something, 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 and then plus 0 times something, 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 something. Again, not even going to bother to look at what those entries are because they're all being multiplied by 0. So I don't care about the entries. Since I multiplied by 0. It's not worth my time. And in fact, of course, I would not ordinarily write that. It's just for those of you following along at home. Why didn't I bother writing them? They'd be multiplied by 0. Okay, well then that makes the problem down to the problem of a 3 by 3 matrix. So minus 1 times, and now we've got the 2, 4, 1, 5, 7, 1, 0, 1, 2. Now the main thing here is find a row or a column of zeros and work from there. As for the other entries, it's not so clear what is good, what is bad, so it doesn't really matter what we do. I'll just take column 1. It's the only column that has any 0. My two choices would be either column 1 or row 3. And the reason why, if you want to know my rationale for picking the one that has bigger numbers rather than smaller numbers, it's been because when I'm doing my little subdeterminants, the numbers involved in that will be smaller. But it's not really a big important matter. But now, again, checkerboard tells me plus, minus, plus, minus, plus, minus, plus, minus, plus. The checkerboard tells me that inside this -1, we're going to have positive 2 times the determinant of 7, 1, 1, 2, minus 5 times 4, 1, 1, 2. And here, just as I work down, I just delete column 1 and row 2 in this case, and next will be row 3. 0 times, and again, if it's 0, not even worth my time. That's the whole advantage of having zeros. Okay, so what do we got here? It's -1, and again, you can do your arithmetic in whichever order you find most convenient. I'm just doing it as it says. So 2 times, and you don't have to write out every step of this, it's just this being one of our first examples. It is not a bad idea to leave a paper trail so you can see what goes where. So then 4 times 2 minus 1 times 1 plus 0. Okay, again, calculators exist, and you can do some of the grunt work that way, but but we can also, these are small enough numbers, we can just figure it out. So 14 minus 1 is 13, times 2 is 26. 4 times 2 is 8, minus 1 is 7, times 5 is negative 35. And so then here, this is going to be negative 9 times negative 1 will make a positive 9. So that is, so that's the way that would go. Now there are some cases where we can cut out a lot of the middleman on this. So a lot of these middle steps here turn out to be unnecessary. In the case of extra simple matrices, what makes a matrix extra simple is not just having a lot of zeros, but having them strategically placed. And in particular, a special case of easy determinants would be what are called triangular matrices. Special case of easy determinants. This is triangular matrices. Now, as we already know, we are only talking about determinants of square matrices. So when I say triangular, I mean that we have all of our non-zero entries confined to either the upper triangle or the lower triangle, as indicated by the main diagonal. So there are two kinds. So upper triangular, and I'll show you what that means. So, for example, something like this: 1, 2, 3, 0, 4, 5, 0, 0, 6. So it's an upper triangular matrix in the sense that all of the entries that are not zero are on or above the main diagonal. So all non-zero entries are on or above the main diagonal. And by main diagonal, we mean northwest to southeast. Then there's lower triangular, which is very similar, just with the change that you would think. So 1, 0, 0, 2, 3, 0, 4, 5, 6, for example. And again, the main diagonal is the key player here. So all non-zero entries are on or below the main diagonal. Okay, well, if we have a matrix that is either upper triangular or lower triangular, then the determinant becomes a breeze. So if A is either upper or lower triangular, the determinant of A is the product of the entries along the main diagonal. So, for example, let's say that for A, I wanted the determinant of what would appear to be a rather complicated matrix. Let's say I had 1, 2, 3, 4, 0, 5, 6, 7, 0, 0, 8, 9, 0, 0, 0, 10. Well, technically, I don't need to use this fact, but it is a fact that I can just multiply the entries along the main diagonal, and that'll give me the determinant. Now, if you don't believe me, you are free to use cofactor expansion, and in this case, you would choose probably, say, column 1 or row 4 in your cofactor expansion. And as you did that, think about the numbers you'd get. So you'd have 1 times, and then the miniature matrix, which will also be rectangular. And then that'll be 5 times the submatrix, which will also be upper diagonal, which will then be 8 times 10 minus 9 times 0. So it's 1 times 5 times 8 times 10, which would be 400. So that was a walk in the park. And an even more special case of an even easier determinant. So thus, let's say we wanted the determinant of the identity matrix of any size. That's equal to 1 times 1 times 1 times 1, however many ones. So this is I standing for the identity matrix. So the identity matrix has determinant 1. Fun to know. So if you are ever in a situation where you need to take a determinant of a matrix, first you should look at whether it's upper or lower triangular, and if it is, then that means you should just cut out all the little steps along the way and multiply together the entries along the main diagonal. Now, this is a little bit off the path of this course, but it's a fact that you might be interested to know. So note. So in vector arithmetic, there is what is called the cross product, and that is typically defined by means of what is called a formal determinant. So note, the cross product of two vectors in R3, also sometimes called the vector product, although technically cross product is the older name and is the more common, is commonly, not always, but commonly defined as a formal, quote, formal determinant. And in particular, if we have u, which is a vector, let's say u1, u2, u3, we'll orient them like this in our first stage, but we can also remember that it's equal to just u1, comma, u2, comma, u3. Oops. So we could also just, so you can orient it horizontally with the angle brackets, and v, which according to us, if it's a column vector, then we usually write it like this, but equivalently the notation can be v1, v2, v3, And then if you remember, there's also the other notation you can use, which is u1i plus u2j plus u3k. And here, v1i plus v2j plus v3k. Then u cross v is equal to the vector that you get when you make the formal determinant that has I, j, and k in the first row, and then for the second row you put in the entries of u, u1, u2, u3, and then v1, v2, and v3. Which, if you were to expand along the first row, it's going to be I times u2 minus v3, u2 times v3, minus v2 times u3, minus j, times, and then it's u1 v3 minus v1 u3, and then plus k, times, and then here what you have is, save that for the next line, plus k, times u1 v2 minus v1 u2. Now, the cross product has lots of uses, lots of meanings. We're not really going to be discussing it in this class. It's actually a class it's a subject that comes up more in a physics class or vector calculus class than it really comes up for us. But if you want to know what it means geometrically, the cross product gives you the volume of the little the area of the little parallelogram that it has u and v as its sides. Or alternatively, if we want what is called the triple vector product, we can do the dot product times of a vector with a cross product, and that will give you the volume of a parallelepiped, which is like the three-dimensional version of a parallelogram. And then in physics, the cross product is involved in such things as the angular momentum or the torque. In the case of something being rotated from a certain radius and it's being rotated at a certain angle, the torque that is applied or the angular momentum that the object has would also be defined by a cross product. It's a strange fact though, cross product is only defined for three-dimensional vectors. There is no such thing as a cross product for two-dimensional vectors or for four-dimensional vectors. Only three-dimensional vectors. And then for reasons of very complicated nature, there is one again at 7 dimensions, but that's way outside the mandate of this class, so you can just forget I said anything. All right, well, that's enough for now for what a determinant is in terms of how it is calculated. So that is the how. Now, what is it for? What does it determine? That's what we'll be seeing in the next section, 3.2. So join me then for the next episode of Math 261. Till then, bye.